Okay, hello everyone. Welcome back to your YouTube channel. This is your YouTube channel. And thank you very much for watching this video. As you must be aware, I am creating a new course, a new training about frequency stability and control in modern power systems. And one key factor in frequency stability and frequency control is the use of power electronic converter based technologies to provide frequency support. And renewable energies, PV and wind power, all those renewable generation power converter base, they can be enabled to produce frequency support if an appropriate control system is included. And my job today, as you can see, I am using Power Factory 2020. And the idea today is that I will be using a very old model that I have here to show you what is the benefit of using a frequency controller in order to enable the power converter to provide some frequency support. But let's start this video telling you what is my plan. My plan is I have a power system, a small power system, generator and load. And in this power system, I have included a model for a battery energy storage system. And I am using a very simple model. Well, not so simple, but a relative simple model for a battery energy storage system. The model that I will be using is resemble this one. Okay, it's basically a power converter. In this case, today we are using a PWM converter, voltage source converter, and this converter is connected to a battery pack. And we are using a relative good battery model where there is a feedback of the state of charge of that battery. And of course, this battery is connected to the DC side of this power converter. On the other hand, I have tried to include as most controllers as I can. For this very specific example, I have included the PQ controller and also the charge controller. But in this case, we don't have a current controller because the current controller is included inside the PWM converter. And what I'm trying to tell you is that the modulation is performed inside the element, the voltage source converter element inside Power Factory. What I am doing is I am including a frequency controller, and this frequency controller is providing active power reference to the PQ controller, active and reactive controller. And then there is a couple signals on the DQ axis going into the charging controller, and from there we are feeding the signals of the DQ currents reference to the power converter. Okay, this is a general overview of the model. In a minute you will see that we implemented this into DIgSILENT Power Factory using different components. Okay, what I will do now is I will briefly describe the network and the network elements in order that you can see the general picture, and then we will go through some of the models used in this implementation. Okay, I must be clear, this is not a DSL training. This is not a training about how to create and settings and tuning controllers. No, this is just a very brief video to show you that power converters can be enabled with frequency sensible controllers and provide frequency support. Okay. Now let's see what we have here. What we have here is basically the single line diagram of the system that we will be using today. As I said before, there is a synchronous generator. This synchronous generator is working as an island. And as you can see, there is a step-up transformer, transmission line going to a bus bar. And then that bus bar is going into the load, okay? On the right hand side here, you can see that we have a step down transformer, well, a step up or step down transformer, depending on the direction. But what it's doing is taking the low voltage from the converter, AC side of the converter, and feeding the active power contribution into the AC system. Here we have a PWM converter, a power electronic converter, and finally here we have a DC bus bar and a DC source that is a dependent voltage source that include the model of the battery pack, okay? On the right hand side here, we have some plots. I will show you in a minute those results. But first, I want that you be very familiar about the model of this battery energy storage. As I said before, we are using a DC voltage source. There is a model inside this voltage source that is providing the signal in order to reproduce the voltage and currents produced by a battery, okay? Here we have the DC bus bar going into this element. This is a network element inside Power Factory. This is the power converter. In this case, this is a PWM converter, and the AC side is going to this two-winding transformer, providing power to the grid, okay? The first thing that you need to see is we are using a very realistic converter. We are using the element voltage source mono, and this is an element inside the DIgSILENT Power Factory. As you can see, the AC side is 400 volts. You can see 400 volts. The DC side is 900 volts. And the total apparent power here, the rate power, is 30 MVA. For this case, we are using a sinusoidal PWM, basically using a two-level converter, okay? There are more details I will not go through because, again, this is just a very short and very demonstrative video. What is important here that you notice is this PW converter, this element voltage source converter mono, has a controller, and if I click here, I can show you what the component is, and it's basically the dynamic model controlling this power electronic device. As you can see, this is basically element composite, and this is coming from a frame that we will discuss in a few minutes. But what I need that you understand is that the network element is the PWM converter, and there are some models and some measurements here. As you can see, we have a PQ measurement. We have a frequency measurement using a classical PLL inside the DIgSILENT Power Factory. We have AC voltage measurement, okay? And then we have DSL models, one DSL model for the active and reactive power controller. We have here the charging controller, and today we are using a very basic inertia controller that I implemented probably 8 years ago or 10 years ago. To be honest, I don't remember. And here finally we have the submodel, and in this case this is the model for the battery. What I will do now is I will briefly show you what is the model structure, okay? Remember, if you are using Rms simulations inside Power Factory, you can build your user-defined models using DSL. And what I will show you here is the frame. This is the general frame for the power converter that we are using today. Basically, the frame is a graph where you can see the blocks that you need to include the dynamic models and the elements, measurement elements and network elements, but also the signal flow. For instance, as you can see, the element going to the network is the element voltage source converter. In this case, is a PWM converter. In this case, we are controlling the PWM converter using the DQ axis current reference, and they are coming from the charger controller. And the charger controller, of course, requires some measurements and some information. In this case, we are using AC voltage measurement, and also we are using the data coming from the battery model. In this case, we are collecting what we call the voltage from the pack, the current from the battery, the state of charge, and the signal, reference signal for DQ currents are coming from the active and reactive power controller. This controller is a feedback control, it's a closed loop control. As you can see, they are PQ measurements in order to define if there is any deviation between the actual active and reactive power production and what the reference is from the active and reactive power. In this model, I just modify and include one more slot here. This slot is for the frequency control. This is a very basic controller, frequency sensitive controller. Is taking measurements from the PLL component, and you get the frequency, you fit into this block, and then you have a reference that you can use for your PQ controller. Okay, now what I will do is I will try to go briefly into the other models, just very briefly. Let's start for the model of this battery. The battery model is very simple. We are using a voltage source. As a consequence, the output of this model will be a voltage signal going into the dependent voltage source. But we need feedback in order to calculate the state of charge and other parameters. For that reason, we are taking DC current measurements, okay? And other very important controller is the PQ controller. As you can see, the PQ controller is defining the DQ axis current reference, and the PQ controller is basically two controllers inside a block. Using the DQ reference, you can have one controller for the active power and one control loop for the reactive power. In this case here, we have inside this block, we have on the top the active power loop. Basically, we are using first order transfer functions, and below we have the reactive power control loop. Again, the input is the voltage and the output is the Q axis reference. For active power, I will explain more about this one, because as you must be aware from electrical machines and from your studies on power electronics, when you are controlling the active power, the D-axis current is basically the variable that you are interested. And here we have a first order transfer function. Of course, there are some limitations, but this transfer function is giving you the value of this reference. But before that, we have here basically error calculation between the reference and the measurement, and delta P is going through a first order transfer function. This summation point here is to take the frequency sensible signal coming from the frequency controller. As you can see, this input over here, this is delta, and that delta is coming from the frequency controller. The P reference represents the change in the active power reference, for the P controller. Finally, we are here, and I am showing you, finally we are here, and I am showing you what we call the inertia controller. I know many of you have read many papers, scientific paper, research paper, and there are thousands of possible ways to create the model of the inertia controller. As I said before, I think this inertia controller I created probably 8 or 10 years ago is very simple. We have here a signal coming in, that is the frequency. Then we have here the derivative component. Of course, you are amplifying noise and so on. And we are using a first order filter here to try to reduce the noise. Then we have a gain, and this gain is basically what we call the gain for the synthetic inertia. Okay, many people call that gain the synthetic inertia, and this model here is a bit different of the Spanish version of this video because I have included a limiter over here. Okay. Now you can see this is one of the implementation, probably one of the worst implementation about inertia controller, but my plan here is just showing you that we can make the converter provide frequency support. That is basically my objective here. And to do so, let me come back to the single line diagram. And what I will do here is I will use RMS simulation in this system in order to show you what is the performance, the frequency response of this power system. Okay. What I will do is at the very beginning, I will go into the controller of the power electronic converter, and I will put out the service the frequency controller. As you can see, I disable the frequency controller, and as consequence, this battery energy storage must be unsensible or not responsive to any frequency change. Then I will run initial condition in this system, and I will show you there is a event, and this event is a sudden load increase. Let me show you. This is a sudden load increase in the shape of a step load, and it's happening at 0 seconds, and basically is increasing 50% this load over here. What I'm trying to tell you is that we are studying here the frequency response of this system, considering a load step of 50% at this very specific load. Okay. Right now, what I will do is I will use the simulation command here in order to run a 10-second simulation, and we got some results. Okay. Right now we have some results over here, but I will go to the big one because here I can show you more details. Okay. As you can see, something very interesting here. The frequency is going down. This plot over here represents the rotational speed of the synchronous machine, but as you remember, the rotational speed is equal to the frequency if we are using per unit system. For that reason, before the disturbance, the frequency is 50 Hertz. Then we have the disturbance, a load increase, and as consequence, there is a deficit of generation. The frequency will go down. As you can see, the frequency reach a minimum value, and in this case, the minimum frequency is 0.985 per unit. Okay. On the other hand, as you can see, also this is the active power production. This is the active power production in megawatts at the terminal of the synchronous machine here. This synchronous machine, that is this plot. This is the output power of this synchronous machine. And if we come back here, as you can see, there is basically a big point here, a big peak, and it's 105 megawatts. Okay. What is happening is when there is a load increase, The synchronous generator is the only generation unit responsible for controlling the frequency, and in this case is suddenly increasing and reaching a peak of 105 megawatts. On the right hand side here, we have some plots coming, some plot of electrical variables coming from the battery energy storage. The first thing that you must notice is that the battery energy storage is unsensible or not responsive to any frequency change. As you can see over here, the active power production is 0 megawatts, and after the event is 0 megawatts. There is a small peak over here, but we can see is almost 0. And the state of charge of this battery stay at the original value, 80%, okay? Now let's do the following. Let me come back here to the single line diagram and let me do the following. Let me write here and let me say the following. Let me take here some text and I will put here without battery energy storage, without the battery energy storage, the minimum frequency, the nadir is 0.985 per unit, okay? Now what we will do is the following. What I will do is I will come back inside the converter and look into the controller, and specifically I will go to the inertia controller and I will enable, now I am enabling the frequency response in this converter by using the inertia controller that we discussed before. As you can see over here in this frequency controller, we have some synthetic inertia, it's a big number, and also I opened the limiters in order to allow the controller to provide any active power without any saturation, okay? And now what we will do is the following. Now we will run initial conditions, and then we will run the Rms simulation. And now we have some results, very interesting results, okay? Let's see over here. Let me delete this, okay? Now we have something very, very interesting. Remember, on the right-hand side, we have electrical variables related to the battery energy storage. The first thing that you must notice is before the disturbance, the active power was 0. Then we have the sudden load increase. The frequency tried to go down, and as the frequency tried to go down, the controller, and that is the inertia controller, the inertia controller calculate the derivative and multiply by a constant. And as you can see over here, instantaneously we have a sudden increase on the active power production in this battery energy storage. In this case, as you can see, we are reaching, let's see, how much is this? In this case, we are reaching 60.7 megawatts, and that is the maximum active power contribution of this battery energy storage during the frequency disturbance. Of course, as the battery energy storage is producing active power during the under frequency events, there are basically two important impacts over here. Very good impact for the network and the system. As you can see now, let's see the frequency, the minimum frequency. Now the frequency is 0.988. Let me go back here to the single line diagram. And now we have battery energy storage, and the minimum frequency is 0.988 per unit. Okay, what I can tell you is this frequency controller is working. This frequency controller is helping. Of course, it's not helping so much, and I will tell you later the reason, but the inertia controller is not so strong helping the minimum frequency. Um, but coming back here to my explanation, if we come back here, this is one of the advantages of enabling frequency response in this battery energy storage. But the other important and very significant improvement that you can see is here at the synchronous machine. Because as you can see, initially, we have a peak of active power at the synchronous machine because the synchronous machine was the only device contributing with active power to cope with the power imbalance. And without the battery energy storage, you must remember that we reach around 105 megawatts. And right now, as you can see, the peak is around 93.2 megawatts. This is a very, very important improvement because that means that you can allow the generator to cope with some part of the frequency disturbance, and then you can allow the most slow and let's say that slowly synchronous generators governors jump in and take over. Okay, however, another final point here, very interesting point here, is the state of charge. Okay, as you can see, previous to the disturbance, the state of charge was 0.8, equivalent to 80%. And then during the under frequency event, this state of charge start to decrease. However, there is something very important here that I need that all my students look at, okay? Okay, the state of charge start to reduce because the converter is taking energy from the battery and delivering active power to the network in order to compensate the power imbalance. However, I don't know if you realize this region over here, around above 2 seconds and let's say 5 seconds in this specific area, you can see that the active power is negative. What is happening is in this region, the Rokov change of polarity or sign. I mean, the Rokov start being negative, but then when the frequency start to recover, the sign of the Rokov change, and now the battery is taking energy from the power system. As you can see over here, we are decreasing the state of charge, but in this very specific point, what is happening here is that the battery start to take power from the grid, and that is not quite good. Okay, during an under frequency event, we don't want the battery taking energy from the grid. During an under frequency event, we want the battery delivering active power in order to try to recover the active power balance. For that reason, I tell you, this inertia controller has many things that they are not quite good. One way to solve this problem is including a limiter here and saying that we will not allow to recharge the battery, but that will be not good enough. To be honest, to solve this situation, what we need to do is include a controller action here, limiting the battery to recharge during the under frequency event. Okay? Well, I think I have demonstrated that the inertia controller is one mechanism that can be included into the power converter controllers and enable the frequency response. This inertia controller probably is not the best. As I said before, this model I published in a paper probably 8 or 9 years ago. I don't remember. Today we have more, I will say better frequency controllers. Please look into my papers and watch the papers regarding to fast active power injection. But the idea of this video was showing you that power electronics, they can be enabled with frequency controllers and they can provide frequency support, and that is very, very important. This was a very short video. I used DIgSILENT Power Factory to demonstrate the effect of this frequency controller. And that is all for this short video. Again, the idea of this video is just to show you that power electronic converters, they can provide frequency support. This video was not to teach you how to use DSL, DIgSILENT simulation language, to create those controllers. Instead, it was just an illustrative example to show you how frequency controllers in power electronic converters can help the electrical power system. Of course, frequency controllers can help the electrical power system, but you need to be able to use the proper controller technique. Well, that's all for today. Thank you very much for watching this video. If you like this video, please go below and subscribe to my YouTube channel, and stay in touch. Thank you very much for watching. I will see you in the next video. Bye now.